Hi there, in this video we're going to look at the Laplace transform of the unit step. We're also going to look at the region of convergence. So the Laplace transform can be written as f of s equals the integral from 0 to infinity of some function f of t e to the minus st by dt. Now we've seen that before and we've derived it in previous videos. Now we're going to look at the Laplace transform of the unit step. The unit step function there equals 1 for all t greater than or equal to 0, and it equals, I'll put it down here, equals 0 for all t less than 0. Okay, so it's going to look like that there. Okay, so there's t, that's a function at 0 here until t hits 0.0, in which case point it becomes 1. Okay, now we know that whenever we do the Laplace transform, it's only from 0 to infinity, so that means that we're not interested about what happens back here. Okay, we're only interested in what happens when t is greater than 0. So when t is greater than and equal to 0 here, this value here is going to be 1. So it's just like saying f of t equals 1. So we can rewrite this as f of s equals the integral from 0 to infinity of our function 1 times e to the minus st, which is just e to the minus st by dt. Okay, so we're interested in this here. So really what we're interested in is the convergence of this function here. So when we're interested in convergence of it, what it really means is when we put in our values from our values of s into this function here, right, then when we allow t to range from 0 to infinity, will we actually get a value for the function f of s which isn't infinity or minus infinity, so we want an actual value. And again, if we then to choose another value for s and allow t to range, then again we want this to converge to an actual value. So that's the question then, is what values allows this, what values of s will ensure that this integral will converge. And remember, s is not just a real, it's a complex. So okay, so it means that if I draw it that kind of 3D, we've got our sigma here, and we've got j omega. Okay, so sigma can be plus and minus, so you're going to have a sigma plus minus j omega, and you're going to have a plus and minus sigma, so it can be anywhere, the number can be anywhere on this plane. So we're going to be putting this number here into this function, and we want to see whether this integral will converge, right? So under what circumstances the integral will converge. So let's go ahead and we'll have a wee bit of a look, a closer look at that. Let me just get rid of this here because we don't need that there now. Okay, so whenever we looked at this e to the s minus st, we can split that into e to the minus st. Well, that's equal to e to the minus, and now s is our sigma plus j omega t. Okay, now that then can be written as e to the minus sigma t times e to the minus j omega t. Now we look at these things separately. First of all, e to the minus j omega t. So we're interested in whether when this thing j omega is positive or negative. Okay, so we've already seen this in a previous video, and I suggest you can go back to, I think it's video number 3 in this series, when I looked at the complex exponential. Okay, so this is a little bit of revision. So what happens is when we have e to the minus j omega t, then this represents a phasor rotating round about a circle, and the fact that it's negative means that it's rotating in an anti-clockwise direction. And if we allow t to range off, then we're going to have the phasor rotating in an anti-clockwise direction and generating a corkscrew along that time axis travelling in an anti-clockwise direction. Now if we were to look at e to the plus j omega t, then we would have the same sort of thing. We'd have an imaginary axis, a real axis, and time. And the only difference now is that the phasor would be rotating in the opposite direction, so it would now be rotating in a clockwise direction. Okay, so the phasor is now rotating in a clockwise direction. But the crucial thing here is that the magnitude of this function isn't changing, and it isn't determined by this e to the plus or minus j omega t. E to plus and j minus j omega t only determines the direction of travel. Okay, so what we are interested in for convergence then is the e to the minus sigma t. So what we're interested in is looking at that function e to the minus sigma t, and we want to see what that function does whenever sigma is positive and negative. Okay, so I'll actually rub it out and draw over here a wee bit further just so we can get in properly. So we have a function e to the minus sigma t, and we have, well, first case is sigma is greater than 0. So if sigma is greater than 0, you're going to have e to the, well, we know t is always greater than 0 as well, so if that's greater than 0 and that's greater than 0, then the whole thing there will be less than 0. Okay, so for example we'll have e to the minus, now if sigma is greater than 0, well, it's just a positive sigma times t, which is just e to the minus sigma t. Okay, now the second case is that if sigma is less than 0, well, sigma is less than 0, you're going to be e to the minus, now it's no longer positive sigma, sigma is now always negative t, so you're going to have e to the, as the two negatives cancel out, so you're going to end up e to the sigma t. Okay, so we're interested in what happens whenever t tends off to infinity in both these cases. So if we draw these out, then we have our t-axis here. Now a function e to the positive sigma t, well, it's going to look like that, just like an e to the t. Okay, so that there is our e to the positive sigma t, and the e to the negative sigma t, it just looks like that, only flipped on this axis. Okay, so it passes at that point. Okay, and we'll come along there, and that's going to be our function e to the negative sigma t. Now we notice that as t tends off to infinity here, we notice that e to the minus sigma t tends towards 0. Okay, so that tends towards 0 as t tends to infinity, and the other one is the other way round about, that's e to the sigma t is the positive one, that's going to tend off to infinity. Okay, as t tends to infinity. Okay, also we note that we're only interested in the values for t greater than 0. Okay, so we're not really interested in anything that happens at this side of the axis. Okay, so those are the only two parts of the function there that we're interested in. Okay, so the reason for doing this is now that whenever we go and we do our integration, then we have our f of s equals integral from 0 to infinity of our function e to the minus st by dt. Now we know that is going to equal, it's going to be minus 1 upon s times e to the minus st, okay, from 0 to infinity. Now we know that it's only going to converge whenever the value of sigma is greater than 0. Okay, so we know as sigma is greater than 0, we get e to the minus sigma t, which tends to 0 as t tends to infinity. Now what's really happening here is that this here is the e to the minus sigma t, it's tending to 0 as t tends to infinity. So what's happening is this corkscrew we see, okay, it's been multiplied by this e to the minus sigma t. So we're going to get, actually I've dropped down there, we're going to get that corkscrew, okay, but it's going to get smaller, 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 so it's going to converge, and the envelope there is our e to the minus sigma t envelope. Okay, so that's the part there that ensures that this little function converges. So, and that's what ensures that the overall integral converges. So we know that we're going to get that value, but we're only going to get that value whenever the real part of s is greater than 0. By the real part of s, we mean the sigma, okay, because that's the one that determines the convergence, okay. So when we finally finish this off, we can then write that as equal to, well, as that tends towards infinity, the e to the minus st is going to tend towards 0, okay, so you're going to end up with 0 minus, and as s tends towards 0, e to the minus st tends towards 1, so you're just going to have the minus 1 upon s, okay, which equals 1 upon s. Now that there's a final answer. The Laplace transform of the unit step u of t equals 1 upon s. But the reason for doing this extra work here is we always have to be careful. You add in the region of convergence, so that's going to be true for the real part of s being greater than 0, and the way you usually represent this here in a diagram like this, where we put in our values of our sigma and j omega, so let that be sigma, let that be j omega. Now we know that there's going to be a pole when s equals 0, so when this value of s, which is our sigma and our j omega, when sigma and j omega is 0, which is that point there, we're going to have infinity because it's 1 upon 0, so we're going to have a pole here, so we put that as a cross, okay, and we know that the region of convergence is for all values for the real part of s greater than 0, that is sigma is greater than 0, so all over here, that's where we get our region of convergence, okay. So it converges irrespective of whether j omega is positive or negative. The value j omega just determines the direction of those phasors, okay. So that's all for this one. Now the next few examples we do will be a bit simpler because we don't need to go through all this other detail here. We only need to do that just once, and all the other examples we can use this little fact here, the real part of s being greater than 0, in order to make it simple. Okay, thank you for listening and goodbye.